Okay, thank you very much. Thanks very much for the opportunity to speak. So I'm going to talk today about rare event ABC-SMC squared, and this is joint work with Evis and Tom Thorne, who are both at the University of Reading. So Evis is going to give part of the presentation a little bit later, and Tom, it looks like, is one of the participants here. So many thanks to our funders, EPSRC and NERC from the UKRI. Okay, so there we go, right. Okay, so here's a quick overview. What we're going to do is we're going to look at a methodology we've been working on that is going to help us do ABC in particular circumstances. So to introduce this, what we're going to do is first we're going to introduce ABC, talk about how you can see it as a pseudo-marginal approach, and then I'm going to go straight into some work that Dennis Prangle last fortnight, 2 weeks ago. Dennis spoke. This is essentially Dennis's idea. This idea of a rare event approach to high-dimensional ABC. I'm going to introduce that idea because, in case people aren't familiar with it, and that's kind of a key thing in our approach. Then I'm going to motivate what we're doing, and we're going to give the details of our new approach. I'm going to give you the approach in pictures, and we'll see how well that works by these slides. And then Evis is going to give you the mathematics behind it. And Evis is also going to talk about some empirical results, and then we'll talk about just some brief conclusions at the end. Okay. So the setting here, I'm sure, is familiar to everyone here. So we're interested in doing some Bayesian inference. We've got a model f sub theta here. So this is a model f that depends on parameters theta for some observed data y. This slide is mostly to fix notation, I guess. So what we want to do is we want to estimate theta, and we're going to do it from observing our data y. And essentially, what we want to do is we want to discover the parameters that could plausibly have given rise to the data, essentially, when we take into account the model and also some other constraints that come from a prior distribution that tell us other information that we have about the parameter. So, of course, the core idea is to find the posterior distribution, pi, of theta given y. But in the ABC setting, the reason we have this method is that whereas usually we can evaluate the model that we have pointwise at theta, and in which case, of course, what we usually do is use a Monte Carlo method to kind of assess the plausibility of different thetas by looking at the prior times the likelihood, as Bayes' theorem tells us we should do. In the ABC setting, we don't have a model that can be evaluated pointwise at theta. So the key thing that we can do is that we can simulate from the model. So if you give me a theta, I can simulate kind of candidate data, simulated data from the model. And this is something that's used in many applications. A particularly pertinent one at the moment is for modeling epidemics and pandemics, including a model that's used in the UK at the moment, which consists of thousands of lines of undocumented C, apparently, which is a model for the spread of flu under different control measures. So the idea of ABC is that we're going to assess, rather than doing this assessment of whether theta is plausible by doing the prior times the likelihood, we're going to assess whether theta is plausible by simulating from the model for the thetas that we're interested in, and checking if the statistics of the simulations are close to the statistics of the observed data. And what we end up using is, this gives us an approximation to the likelihood, which we'll call the estimated ABC likelihood, and the posterior we'll call the ABC posterior. So some of the key challenges in ABC that people have been working on over the last 15, 20 years, or however long it is, are, well, one of the key ones is how we explore the space of theta. So there was a lot of work in this area done sort of 15 years ago or 10 years ago. And there are different methods for doing that. Rejection sampling, importance sampling, MCMC, SMC, Bayesian optimization more recently. And then another important challenge is what's the effect of using this approximate likelihood? And essentially there's two issues there, roughly speaking. What we want, one is bias, so that we use some summary statistics rather than using the full data, which gives us a different answer. And also that we have some tolerance epsilon that I'll introduce on the next slide, actually. And this introduces a bias into our posterior. And then we also have variance. It also introduces variance compared to using an exact likelihood. So essentially, because we're estimating the likelihood rather than using the exact one, there's some variance associated with that, and that gives us extra variance in our estimates. So we're gonna look at ABC-MCMC. I'm just going to introduce this approach, and then we'll sort of talk about this stuff about the effect of approximating the likelihood through looking at that method. So ABC-MCMC looks like this. Again, I'm sure most people are familiar. The notation we're going to use for the way of comparing y to x is pi epsilon. So pi epsilon is such that it's bigger when y is closer to x, and as epsilon gets smaller, we get more and more concentrated. This thing gets more and more concentrated, so essentially we only get a good score when y equals x. Okay, so this is like the usual kind of comparison of y and x. So ABC-MCMC works like this. You simulate candidate values of theta, you have a chain, and you simulate your proposed value theta star, and then you simulate some new data at theta star, and then you have this acceptance probability where we have this pi epsilon here. Now, if you compare this to the usual Metropolis Hastings acceptance probability, we usually have a prior times a likelihood, and here we've got a prior times pi epsilon. So essentially, it looks like pi epsilon for this x that we've simulated is playing the role of the likelihood, and we can see what's going on like this. We can think of essentially this method as using essentially using this likelihood here, which is this integral, and what we're doing is we're estimating that likelihood at every step. And the way we estimate it is, well, it's like a standard Monte Carlo estimate, but we're going to phrase it as an importance sampler because of what's to come. What we do is we simulate some x's. So essentially we're simulating from this distribution here, and then we're evaluating this function at the points we've simulated. So it's just a standard Monte Carlo. Someone's just flipped. There we go. Right. So it's like it's a standard Monte Carlo estimate essentially. So essentially here, what we're doing is we're plugging in a likelihood estimate into the MCMC. To lower the variance, we could take multiple important points here, multiple x points, to get a lower variance estimate, and that's the one that we're in fact going to use. And what we're going to do is use the uniform kernel. So essentially, this pi epsilon is either 0 or 1, or 0 or something constant. We'll think of it as 1. So then this likelihood estimate is essentially the number of acceptances when we simulate multiple x's. Okay. So why does this work? Well, it comes from the I mean, it was proved before this, but a nice way of seeing it is through the pseudo-marginal idea, which is that we can plug in any unbiased estimate to our real likelihood instead of the true one, and we'll get an unbiased answer. So we're unbiased in the sense that we're targeting the true ABC likelihood is of course itself still biased. So we don't get any additional bias for this, but we do get some extra variance, and that makes our ABC-MCMC less efficient, essentially, than if we could use this true integral. So what do we do about this this variance? Well, the variance is going to increase when the dimension of y gets bigger, because we're doing essentially an importance sampler in high dimensions. So so in fact, we need an exponential number of points essentially to cope with the dimension increasing in y. and it's going to get, the variance is also going to increase as the tolerance decreases, because the target is further from the proposal, essentially. So ways of getting around this, that we're all familiar with, are introducing summary statistics to reduce the dimension, or sometimes we have to resort to a larger epsilon, whereas we'd like to shrink epsilon to 0 to get the least biased results we can. Essentially, we sometimes choose epsilon bigger than that to allow us to cope with the variance, essentially. So what are the alternatives to these approaches? So the thing that we're trying to avoid here actually is this use of summary statistics. It introduces some bias that's quite difficult to get a handle on. So can we develop techniques that don't need to do this and can do high dimensional ABC? Well, the method that we're going to rely on here is one that I think originates in a discussion by Christophe Andrieux and Arnaud Doucet and Anthony Lee on Dennis's red paper at the RSS. And this is a construction that's used in a number of other papers. I've provided a link to a draft paper, and all of our answers are in that draft paper, by the way. So if you're interested, then go and have a look at that. That's in the chat on the live session. So this is a way of seeing ABC that allows us to do some things that we wouldn't usually be able to do. And the idea is that we see our simulator as a deterministic transformation of the parameter and some random numbers, so a random vector u that has some distribution phi. So essentially, that we're not changing anything here. We're just rejigging or looking inside the sort of black box of the simulator that we usually have, and looking at how it's structured. We're looking at firstly the random numbers we generate, and then the deterministic transformation of those that gives you the simulation. And I guess the idea here, what does this allow us to do? Well, in standard ABC, one of the problems is that when you simulate from the likelihood, you do it sort of independently every time you look at a different theta. So you sort of, it doesn't matter whether you found that a certain configuration of the random numbers in the simulator worked well for a nearby theta. We sort of ignore that in ABC usually. We just resimulate from the likelihood and pretend we don't know about that. But when we have this formulation in terms of unpacking this black box and looking at these u variables, we have the opportunity to move around theta and u space and essentially tailor our u's to the different thetas. And the approach we're going to focus on here is this idea introduced in Prangal et al. 2018, the one I mentioned, the rare event method. And the idea here is to do something that's essentially the pseudo-marginal, well, essentially particle MCMC, but in the ABC framework, where the u variables here play the part of the variables that we're going to integrate out. So in this paper, it describes essentially how to do this. You use a sequential Monte Carlo to estimate the ABC likelihood rather than the importance sampler. And we know from the theory that this should have a lower cost to control the variance, essentially. And the nice thing is that it scales quadratically in the dimension rather than exponentially. And so that should allow us to tackle higher dimensional problems. So a key point here is this is not ABC-SMC. ABC-SMC is an SMC on theta, and well, it's essentially like it's on theta space, but to show how it works, it's essentially on theta u space. And what we're doing here is for different thetas, we're doing SMC over u conditional on theta. We'll see how that pans out in a minute. So here's the rare event SMC stuff. What you do is for different thetas, so this is embedded in an MCMC. So you choose a theta, and then you have a initial distribution in your SMC that's conditional on theta. That's just the proposal distribution on the u variables. And then what you do is you have a sequence of targets where we introduce this pi epsilon, firstly with a very big epsilon, and then shrinking to the value that we want. So it's like doing the importance sampler. The importance sampler is like starting from here and going straight to the end point, but essentially here we have many intermediate points. And the algorithm ends up looking, so when you calculate the weights in this algorithm, they all end up to be 1 and 0, and you end up with a likelihood estimate that is very simple in the uniform kernel case. All you have to do is you take the product over all of these SMC iterations of the average of the weights at each step, and essentially the average of the weights at each step is going to be the proportion of particles that were accepted or got a non-zero weight. Sorry. So we end up with this SMC approach. We end up with a very simple likelihood estimator. So here's a picture that's ripped from that paper. Apologies to Dennis for using his picture here. And this sort of is a rough picture of what's going on here. So to start with, we draw. This is our U space here. So we draw. So all this is conditional on theta. This is what we do to decide whether we want to accept a theta or not. We draw a bunch of U variables, and then we look at the ABC kernel at these for the first epsilon and see which ones of these get a non-zero weight. Those are the red ones, and all the other ones get a zero weight. These are the ones that are close to the data, or result in the deterministic transformation being close to the data. And then we do standard thing in SMC. We resample and then we move. So we resample, then we do an MCMC move. And that results in the blue points here. Never mind what's going on with all these arrows at the moment. It results in the blue points. So the blue points are kind of better starting point for the next step than the black ones. And then we repeat what we're doing. Okay, that's the rare event method. Okay, so to set up what we're doing, the point is that the rare event ABC-MCMC, so this is like a particle MCMC essentially for ABC, is a nice method. It helps as the dimension of the data grows. It works well, but we don't have the nice properties of ABC-SMC, which I haven't introduced yet, which is that we have a population of points for exploring theta space, and we can adaptively change the epsilon as we move through the algorithm. So hopefully people are kind of familiar with the approach. It's like starting out like an ABC rejection sampler, but then using one epsilon and then using the points you get to help you in the next stage. So on theta space. So you're doing an SMC on theta space. So what we want to do is combine this ABC-SMC with this likelihood estimate from the rare event method. So what I'm going to do is try and explain the method that we come up with these pictures. So Evis is going to explain actually what's going on, but I'm going to try and explain in pictures what's going on. So the key thing to compare with is ABC-SMC. So I'm going to start with ABC-SMC, see what that looks like, and then we'll see what our approach looks like, and then Evis will show you where it comes from. Okay, so we start out with by drawing some theta points. So this is candidate values from our posterior, and that's these blue boxes here. Okay, and we've got two of them. So we've got two particles in our ABC-SMC for simplicity. And what we then do at the first step of ABC-SMC is simulate some U variables. Now the U variables here, these are like the X variables in standard way of formulating things. That's these black points here, okay? And then what we do is we do a weight update based on our first tolerance epsilon, okay? So the prior that we drew these things from, the initial distribution, the initial simulations from the likelihood are in the black box, and the first epsilon here is the red ball, okay? So our weights are, this is essentially like I'm showing you on a bigger picture what I showed you. It's a bit like the picture I showed you a few slides ago as to what's going on the kind of simulated data space. So what we do here is we do a weight update. So the ones inside the circle get a non-zero weight, and the ones outside get a 0 weight. And that gives us the weights for our, that gives us the likelihood estimate, which gives us the weight of these two theta particles. Then at the next step of ABC-SMC, you take these, so the key thing here is to look at the black points. You take the particle in theta space coupled with these black points that you drew last time, and you use these black points again to get you an estimate of the ABC likelihood with the new tolerance, okay? So, and then we update our weights for our thetas based on this weight update here, okay? And at this stage, I'm actually going to show you the other steps of the ABC-SMC I sort of missed out. What happens on this theta space is that we then look at these weights of these thetas and we resample, and then an MCMC move on theta. So that's what we're going to do now. If I can press the right button. There we go. So what's happened is that both of these particles survive the resampling step, these two theta particles, but we're going to propose a new value for this particle here. Okay, so this is our MCMC move. We're proposing a new theta value. We're going to ignore this one over here just for simplicity. So we propose a new theta value, and that comes with its own collection of variables in data space. Okay, and it turns out that more of these things fall inside this circle, so our likelihood estimate is better here than it was here. Okay, so this thing is going to be accepted. So instead, at the next iteration of our ABC-SMC, this particle here has switched to this value of theta over here. Okay, and that comes with the u variables here that come from this picture here. And then we use these u variables here, the things in the data space, to estimate the likelihood again, and that gives us our weight updates and etc. We carry on. So that's ABC-SMC with a sequence of tolerances that start out big and get smaller. So the problem with this approach is that you can see that by the time we get to this point here, we're not getting many points within our epsilon ball, and these likelihood estimates are going to be high variance. Okay. So this is why ABC-SMC and all these approaches that use the ABC likelihood estimate eventually stop working as epsilon gets too small, because the likelihood estimate is eventually going to be high variance. So with the new approach, we start out in a similar way. So for those who know SMC squared, so I know at least two of the participants here will know it extremely well. So you can probably go and, I don't know, watch Netflix for 5 minutes or something, because you know the SMC squared algorithm. But for those who can't remember or haven't seen it before, this is what's going on. So this is what our method looks like. We start out in the same way. We start out with some points in theta space. Then we simulate points in the data space, the u variables, and we use these to calculate the weight update. So everything up to this point is the same. But then what we do is we're using the rare event idea, and things are going to change a little bit. So the next step is that we are going to do some resampling and then MCMC moves on the U space. This is what was going on in the previous picture that I said I'd stolen from Dennis. And this is essentially the result of doing the resampling and then the moving. And you can see that the particles that were outside the epsilon ball got 0 weight, and so they didn't survive the resampling, and we duplicated some of the ones we had, and then we did MCMC move, and we end up with things inside this ball. Okay, and then what happens next? We do the similar thing as we do in ABC-SMC. We move on to the next step. We keep the key thing here is to look at these black points here. These black points are now the ones, not that we started out with as we would have in ABC-SMC, but they're the black points that we got from the MCMC move last time. Okay, and then what we do is we use this to calculate. In fact, in this algorithm, it's not just the likelihood, it's the likelihood ratio of using this epsilon compared to this epsilon here. And that's a key property of this approach, as well as doing this MCMC move. That's essentially the difference from ABC-SMC. There's the doing the MCMC bit here, and the resampling in the MCMC, and there's the fact that we're using this to estimate the likelihood ratio rather than the likelihood. Okay, and then what we do is we do our resampling and then MCMC on these points. And then we're going to do our MCMC move on the thetas. So I'm going to ignore this one again. I'm just going to see what happens when I propose a new theta for this one. So it's going to work very slightly differently. It's a bit more expensive than the ABC-SMC because we have to start from the start and then follow this through. So what we do is we start out for this new theta that we've proposed. We draw some extra u variables, just like we did in ABC-SMC, but then we do the resampling and MCMC, and then we use this to help us calculate the likelihood of the new theta star, and then we process the u variables again, so we resample and move them again, and we end up with these ones here. So our proposed new theta has to go through this entire process, which in fact is just a particle MCMC. It's like a rare events ABC-MCMC move on this theta up to the current epsilon. And through this process here, we get the by combining this thing here and this thing here, we get the likelihood estimate for this new theta. And it turns out again that we accept it, and so we end up with this being our new theta point. And then we estimate the ratio again of the ABC likelihoods with different epsilons. So you see that what's happened here is that these estimates here that we get that are composed of doing this, then doing this, then doing this, should be lower variance than just estimating it as we did before. So this is the key difference between ABC-SMC and our approach. It's doing these MCMC moves and estimating these likelihood ratios, and that's going to give us a lower variance estimates for our likelihoods, and we're going to end up with a more efficient algorithm, a more efficient SMC algorithm on theta space than ABC-SMC. Right, and now Evis is going to take over. Sorry, I'm very slightly over time, but I think we're still within our time slot. Okay, so Evis is going to take over and explain some of the maths behind this.
Okay. Hi everyone. Thank you, Richard. So yeah, again the same here. Author. So I'm going to skip that slide. So yeah, we're going to go through just as a bit of like a slight background, just going through the SMC squared algorithm, not in much detail. Everyone that's interested enough and that hasn't read it actually is invited to actually read it. It's an extremely interesting construction and algorithm in general. Then we'll just go through how that is adapted in our case and sort of solidify it, make it a bit more concrete based on what Richard just described previously. A bit more detail into how actually it's implemented, and then some preliminary results. So again, now the SMC squared and in general the issue with that is, or sort of the birth of that, she has a long history, but a few very basic facts that pretty much everyone knows, but I'm going to reiterate them. Since important sampling, first of all, results in exponential t increase in the variance. In some cases polynomial, but that's for very simple particle filters. You know, it's impossible to compute the likelihood directly. The autocorrelated state space is high dimensional, and the parameter dependence on a sort of a regular Gibbs sampler is a fact. So on the other hand, MCMC is limited in sampling from the static space, which, given the latent variables and the observations here, would be a very large dimensional. So the idea here is to move to more sort of sequential or recursive. Now, the original idea was due to these authors, which combines the iterated batch importance sampling of Chopin on the theta space, and then an SMC to estimate the intractable likelihood on the heat space. Now, that's a sort of an example of a random weight particle filter, but let's not get into that too much for now. The idea here of the iterated batch importance sampling, just as a small comment, is on sequentially and recursively actually incorporating more of the actual observations wise here in batches, and hence estimating the thetas and or doing inference of the theta space in that way. So then the main problem here is that inference in both parameter and latent space is very hard, either because of the high dimensionality in both of these spaces. So based on the development of the particle MCMC methods and the fact that you can actually use an unbiased estimate of the marginal likelihood in place of the intractable likelihood there, we can make the entire thing work. And then the theta particles are actually properly limited. It sort of allows, again, as I said, the recursive exploration of the sequence of parameter distributions by n theta weighted particles. Now, in our case, the scenario is a bit different, but let's step a bit back into the ABC. Again, Richard already touched on those, but just to sort of reiterate them a bit more in detail, you will need the number of points would scale exponentially dimension. It's a very nice result, some of the results based on quite a bit of literature before by Gabriel in 2015. And with epsilon small, we would need, again, exponential number of points to get an acceptance. See Dennis' paper. Now, of course, there are other methods better than importance sampling, as an importance sampling SMC, which Richard explained already. And in this case, there are event SMC which can bring that cost down to quadratic, but with a small caveat of actually you being able to actually find the deterministic transformation to transform from the EU space theta. So again, instead of using SMC for experimental parameter space, use SMC here with all the regular benefits, better multimodal distributions. We don't need to set a particular epsilon up front. The exploration can go sort of in a smoother function because we get through a smaller epsilon. And again, here, as we started today, it's the same idea of SMC over MCMC, whereas here SMC squared would be the equivalent of particle MCMC since it uses an unbiased estimator. And here, again, the equivalence being that instead of the rare event-based particle MCMC that's used in Planck paper, we would use the exact sort of, not exact, almost exact equivalent of SMC squared for particle MCMC. And again, just to compare and contrast them a little bit, again, the internal target of SMC is conditional theta, the latent variables, then the actual model, or the update. Updating to the next iteration, we add the new one, and we estimate the ratio needed for the state space, for the theta space, for the parameter space SMC. In ABC instead, we will have, as I just explained already, the ABC likelihood, and the updated the next step will be actually the ABC likelihood ratio instead of just the ABC likelihood. Again, in sort of almost their equivalent to the SMC squared idea. So, okay, now the sort of intuitive understanding of what the rare event SMC does was explained previously. So let's get into the actual algorithm. Again, this is the adaptive version, but it's sort of easily to go back, say, to the fixed schedule of tolerances epsilon. Again, we calculate epsilon t and how you calculate in the adaptive ABC-SMC case, which is you pick certain proportion of particles that you want to survive into the next iteration, and you calculate the epsilon such that that condition is satisfied. Then you calculate the weight, you calculate the weight, you normalize, then you resample with a method of choice, whatever it is that you want, and then you move these particles with some, I would say MCMC move here, and that's sort of theoretical, but in actuality it's not a Metropolis-Hastings move. It would be more of a slice sampler here, because again, just to reiterate, the internal area SMC is on U space. It explores U such that it's tailored for a fixed theta and a final epsilon, such that all these U's are tailored exactly such to produce the lowest or the desired epsilon closest to that theta. And again, that's the internal one. So how does that fit into the external one? Well, again, in the same fashion, I should mention that the adaptive sequence of epsilons here, calculated adaptively in the same way, it's the same. We move through one epsilon at a time, such that it's not the case that the internal rare event SMC moves with a different schedule than the external one. The schedule is the same, adaptive, but again the same. So again, the difference here is that for every theta particle, we calculate the ratio of the ABC likelihoods. We update the weights. For some degeneration criterion, we resample and do an MCMC move. I will say a bit about the CSS here because it's not the regular effect sample size that we are concerned with due to the adaptive nature of the algorithm. And again, we replace the correct particle system, we sort of normalize the weights, and again, it reiterates until we reach a certain epsilon, which we might have fixed, or I mean, we can even stop it online since it's one of the benefits of these type of algorithms. So now, just a small comment, we use actually conditional ESS instead of ESS since we are in a full adaptive scheme, and we sort of, since we are not resampling every step, which I suppose we could, but we're not sampling at every step, the sequence of, or the successive sequence targets and what the ESS measure as a discrepancy between them is not exactly the same if we don't resample at every time step. So we use a conditional ESS, which again, you're invited to read the paper by Johansson on that, which is actually the correct thing to do in these adaptive scenarios. So again, just to make it clear, the ABC scale says exponential. Here, the rare event SMC ABC scales.
We can't hear you now, Evis.
Can you hear me now?
Yes.
Oh, okay. Right. Where did I leave?
I think it was just as you got to this slide.
Okay. Well, anyway, so what is we are going to stick with the same model that was used in Prangle et al. Paper, just for the sake of comparing the same things, which is an IID Gaussian, and the actual parameter value here is sigma, and it's a 25-dimensional one, a state space. And we will see how even that sort of in the ABC context, I suppose it would be considered high-dimensional one, but we will see just because of this algorithm and how it incorporates into the SMC squared umbrella, it can actually scale it further. So here are just some results from Prangle et al. Prangle's paper, which should have noted. The left one is just a threshold, the epsilon, and the root mean square error, which again just show that the actual posteriors are correct. The right-hand side is again the threshold epsilon, but plotted again with time divided by ESS to show that for the same computational effort, we get a better result. And you could see the cluster here of variable, which are the standard ABC and the ABC-MCMC, compare both the adaptive and the fixed schedule rare event ABC. Again, keeping in mind that this is the particle MCMC here scenario as used in the paper, and we see that it actually performs much better. Especially one, it can go into smaller epsilons for that reason, but either it can perform better for the same scenario or go into smaller epsilon. Now to stick with that because I'm sort of running out of time. Now this is sort of an important thing, and this shows the entire scaling of the algorithm. This is the adaptive rare event SMC. Again, nothing new here other than the rare event stuff. And it shows that for a given epsilon, which here would be an epsilon target of 3, how long does it take, how many iterations does it take of the rare event, of the adaptive rare event algorithm to actually reach that epsilon, such that it can tailor the use for that theta. Here I should mention that here we supply the actual true value of theta, so that we know that it can actually get into whatever epsilon we want fairly easily in a sense. And we see that for 2 dimensions, which is what originally proposed in the paper, which is sort of high dimensional enough, it takes very few iterations, around 70. Double dimensionality, it goes to about 180. Quadruple dimensionality goes to a little bit above 500, and so on and so forth. And again, you can see the effect that coming from exponential in scaling to quadratic has in this. Now, of course, this is not the direct comparison, because this is not the quadratic scaling. It's incorporated into the rare event, into an SMC algorithm, the rare event one. But it's also very obvious that even take, for example, a fixed epsilon level here, whatever level you want, however arbitrarily small. Of course, the time it takes to reach that epsilon will increase, but it will definitely increase in a much smaller fashion than the exponential one, the regular ABC would. And that's again due to the rare event algorithm and how that tailors the use to the theta. Just another important thing to notice, again, the adaptive rare event SMC here, just for a different, how many particles do you want actually to keep when the algorithm sort of iterates and calculates the next epsilon. We see that if you want to keep 90% of the particles, at every iteration, well, the difference is quite stark in this already much better scenario than standard ABC. But if you are fairly strict on how many particles you keep, you can get a very low index on how low the actual, how many iterations the internal algorithm can take. And again, remember that we're talking about the internal algorithm, which runs for every particle of the external one in theta space. So you would probably want to minimize how many iterations it actually takes to reach a certain epsilon. And keeping in mind that the adaptive schedules is the same for both algorithms, internal and external one. But to reach every successive epsilon, the internal one has to be sort of quite efficient so that it doesn't delay, in a sense, the external one. Now, again, given that it requires sort of little fine-tuning, but given that appropriately, you can go up from the 25-dimensional case here. Yeah, we can go sort of fairly easily up to 400, which is already very large for ABC, in the state space. And we will obviously be quite prohibitive to do for regular ABC. And now, the next point of comparison, since it was the main comparison at the end of Richard's part, how does it actually compare to ABC-SMC? Well, again, as expected, given the much better performance of the rare event SMC, which uses the ratio of the ABC likelihoods and tailors the use to the thetas, the parameter space exploration, is that for a given time, it can go down to much lower epsilon. And just as a final note before I give it back to Richard to finish off the presentation, this is, again, expected, but also keeping in mind that here we're dealing with a fairly large parameter space, a fairly large state space, but just a one-dimensional parameter space. It seems to be the case, or at least intuitively, even if when you actually increase the parameter space as well to some degree, some reasonable degree, this graph here will show an even bigger improvement. The ABC-SMC squared will actually be even better than the regular ABC-SMC. Again, because of the gains of the internal likelihood approximation of the ratio of the likelihoods and the getting down of the exponential scaling to the quadratic and how few actual steps that needs to get down to certain epsilon, it will fit into the bigger external SMC parameter space exploration algorithm and would actually make it even better. So the effects we can say are cumulative here, obviously. So I'm already running over time, so I'm going to give it back to Richard to finish off the presentation.
Okay. Yeah, so really, I'm just here to wrap up. So so what we've done in summary, hopefully that through the pictures I was presenting at the start, hopefully they work to some degree, and Eva's telling you what's actually going on. Hopefully, it's kind of clear what we've done. So what we've done is we've taken this rare event approach that was in the Prangal et al. Paper that was used in the ABC-MCMC context, used for getting low variance of the estimators of the likelihood, giving you more efficient algorithms and letting you scale to higher dimensional data. We've taken that and plugged it into the ABC-SMC framework. So compared to ABC-SMC, we should get all the advantages. I mean, from the last figure that Eva showed, we can deal with high dimensional data. Of course, we are sticking places where we can write the where it's useful to write the simulator in this form. And then compared to the rare event ABC-MCMC in the Prangal et al. Paper, I guess the thing that we're hoping to gain is that we've got this really nice thing where we can adaptively choose epsilon, and that we can usually now reduce that to being quite small. And we can also, of course, estimate the marginal likelihood. And so the empirical results are promising, but as you might be able to tell, this is not finished work. So we've provided a link to a draft paper in the chat here, and this is one of the things that Evis is working on for his PhD. And so any feedback that any of you have would be yeah, really interesting to find out what you think. Okay, thank you very much.
Okay, many thanks, Evis and Richard, for your talk. A lot of virtual clapping. So this is Michael Goodman from the University of Edinburgh speaking. I'm moderating the Q&A. Please use the raise of the hand icon to just raise your hand so that I can give you the floor to ask questions. Okay, first question by Umberto.
Hi, Umberto.
Okay. Hi, Richard. Thanks both for the presentation. I was just wondering, something that you slightly mentioned, and maybe I misunderstood it. Did you at some point say that between the MCMC iterations, you reuse the auxiliary variables, so they use corresponding to the particle that you accepted? I'm not sure if I misunderstood that, or you actually said that.
Is it on one of these pictures? So is it on this picture?
I think it was slide 20, but doesn't matter really.
Slide 20. Okay, let's have a look.
It's not something that was written.
Let's have a look. So this one in the ABC-SMC. Is it in this part here?
Yeah, it was in the slide. Yes.
So is it the bit I'm pointing to with the pointer at the moment?
Yeah.
Yeah. Okay. So in the global view of the algorithm is you've got particles in theta space, and you do the standard SMT things, which is your reweight, your resample, and your move. And so so this bit is meant to be representing the reweighting, and the resampling is absent from here because it would make the picture messy. And then then there's a move step, which is an ABC-MCMC move. So what's happening in that move is that you so we're only looking at it for this theta 1, theta superscript 1 particle. So this is our current particle with our current likelihood estimate here, and we generate a new theta with a new likelihood estimate. And all that's happening here is that we're doing an accept reject step, and this one here has a higher probability than this one, and then this one becomes the new value for that particle essentially. Is that so? I realized that did that answer your question? Is that clear, or is that not answering your question?
No, my question was related to the auxiliary variable, so the U. Yeah. I thought that at some point you said that you reuse the U's that correspond to the particle you accepted.
Yeah. So essentially, okay. So maybe this answers it. Maybe it doesn't. So although we think of this algorithm as being on theta space, to kind of see what's really going on, you look at it on theta U space, and so every one of these thetas is coupled with a U variable, and the thing that is the difference from the next approach is that these U variables are always once you've drawn them for this theta star, then those U variables are the ones for that particle, and they don't get refreshed until you get another theta essentially. So these black points here are the same as these black points here when it's part of the algorithm, and these are the ones that are used for the likelihood estimation.
Okay, so you're using a correlated particle filters approach essentially.
So it's just, I guess it's just a random weight SMC sampler where the variables used to calculate the random weight are these things here, and because it's a standard ABC algorithm, the only way of refreshing the extra variables that we've generated is by simulating from the likelihood. And the only point at which we do that is when we simulate a new theta.
Thank you, Richard.
Okay.
Okay, Nicola.
Hi, Nicola.
We can't hear you. You may have to unmute your mic, Nicola. No, I at least can't hear you. You can just use the chat maybe to ask the question.
Yeah, that's fine. Okay, right. So when do we do SMT for a rare event problem? So, okay, sorry. You have to do MCMC steps. Yes. Okay. Yes. Right. Okay. So, yeah. So we sort of skipped over that. Evis mentioned it. So when this is something that Dennis looked into in the precursor to this paper, the MCMC one. So so he found that slice sampler worked well, essentially because as you say, you're operating under these constraints. So if that's on the next couple of slides, I'll just skip forward. So this is the rare event algorithm here. So if you're going to simulate from this constrained thing here, then yeah, the slice sample works well. And the reason that you need that is that if you could try and do some kind of adaptive MCMC thing within the SMC, but yeah, the slice sampler worked well essentially because yeah, you have this problem where the kernel that's suitable at this point isn't going to be suitable at the next point. And the slice sampler was one that he used.
Okay. Any other questions? While people perhaps think about questions, let me ask one. So actually on this slide, you mentioned that you needed to estimate or use the likelihood ratio.
Yeah.
Can you explain briefly why you need it and how you do that?
Yeah. Okay. So so if you in the kind of external SMC algorithm, your okay, so yeah, so in your SMC algorithm, your weight is on your theta particles is kind of going to be based on the ABC kernel, the pi epsilon at this one divided by the pi epsilon for this one here. Okay. Well, again, they're both on this picture, right? And the weights are going to look like that. So if you look at what the weights should be in your external SMC algorithm on theta space, that's what the weights should look like. And I guess the thing that this way of formulating things gives you is that by taking the particles that you have in U space from the previous iteration and doing essentially you're using them like an importance sample for the next step, and it's in an SMC sample to get what we need in the external algorithm is the ratio of these essentially ABC likelihoods. We've got a ready-made candidate for estimating that, if you like, which is the U particles at the previous step, using them to estimate the thing at the next step. Does that sort of make sense? It's so in an SMC sampler, when you estimate the normalizing constant of the entire thing, it's composed of sort of a ratio of the first distribution with respect to the second. We're talking unnormalized distributions, and then the second compared to the first, third compared to the second, etc., etc., etc. And the points you use to estimate those ratios of normalizing constants are your state of your SMC sampler. And because in the original SMC squared paper, it turns out that yeah, you need the likelihood rate, the weights of the external particles need to be this likelihood ratio, and the way you calculate that likelihood ratio is the is using these internal points on U space.
Okay, got it. Thanks. Thanks.
So some questions in the chat. Yeah, so Evis answered this one. So David Frazier said, what dimensions in the parameter space do you think this will be scalable to in practice? And Evis answered, I mean, yeah, it's difficult to put numbers on it. It depends on the example, really. I mean, it's only a very simple example that we got this scaling to up to 400 dimensions.
Can I just mention that?
Go for it.
Sort of, yeah, I mean, in the same sense, we sort of have to be considered in, I mean, jointly, in a sense, like parameter and state space So you can have like both of them like widely increasing. So here we sort of say the state space, since it's in a sense where the U and then feeding into the theta would operate, would directly feed into. But then again, in the theta space, you would need again, it's become sort of obvious, but then you would need the U's, which we're doing the relevant SMC for, to feed many thetas, or to try to tailor the U's into a very high dimensional theta. So I don't know how much sense that makes, but then research can.
So yeah, so I think you're right. I mean, so I wouldn't like to put a number on it. I'm not sure. I know that I think in the original paper on this, Dennis found that if you increase D too big, then it's still too hard. It's difficult to completely get away with using no summary statistics ever. But you could use higher dimensional summary statistics. And I guess what Eva is saying is, if you have a higher dimensional data and you don't have to reduce the dimension through summary statistics, then we hope that that would lead through into being able to use higher dimensional parameters as well, which often we can't do because we reduce the dimension of the statistics, which means the parameters wouldn't be identifiable.
Exactly.
Dennis has posted a link to the paper that we got the slice sampler from. Umberto said, so you can only deal with the case of having H of U and theta at the moment. So he's asking if there was a possibility for an extension. I don't see that at the moment, but I'd be really interested if anyone had any ideas. And I think that is all the questions.
Okay, let's thank the speakers again, because we're already a little bit over time, and we will then have the next seminar in 2 weeks' time. So thanks again, Ivis and Rich, for the great talk.
Thank you.
Thanks for listening.